Hello, Team 3 Circuitous and Team Tomasulo are here to present you our TTT Hardware Firewall. To demonstrate the working of our hardware firewall, we will exemplify it using an animation. So let's go with it. We present the story of Mark, the airport guy. Mark used to work at the LAX airport, and he was responsible for handling the incoming traffic at the airport. He was a nice guy. He just wanted to win an award for the LAX. The security was at risk, and he had really less resources. So he employed a common system, placing an officer to check the incoming passengers. He checked the IDs of the passengers, but meanwhile, there were lines getting stacked up to get inside the border, and with some fringe elements too. The ID of the passenger was then ran through the system with random names on it, and if the passenger's name is highlighted on that, then the passenger has to go through one more round of check, which is a lot of overhead. Bad, right? But this created a lot of overhead too, because people were getting piled up again and again. So Mark thought of letting some people go to get the queue moving. Well, you remember that guy who had the knife in his pant? Yes, that guy named is Carlos. And he gets away because his name was not in the system. So he's perfectly able to smuggle the knife inside the border. Pretty screwed up, right? So Mark's become tensed because the smuggling rate kept on increasing and the reputation of the airport went on decreasing. He then saw an advertisement of a TTT company, which is best in providing airport solutions. He goes to see them, and they advise him to buy their triple purpose scanner. It scans tickets, IDs, and the people. That system was employed at the airport. This is the system, and the people went through. There was no overhead, and the lines were getting really faster. Remember the guy who got the knife first? Now he brought a gun. He went to the system again, thinking that he might get out of this, but there was an officer monitoring everything, his body too. So he was caught and was sent to the jail. Mark saw great results, and the smuggling rate decreased by a margin, and the airport reputation went really high. Both were happy. Amid with the scanner performance, he thanked the TTT company, and of course, he won the award. So our system emulates the working of that scanner, which was installed at the airport.
Now let's see how our hardware firewall works in the network system. We have a setup in which there is a good client, there is a bad client, there is a honeypot server and a designated server. Our firewall sits in between them. Let's see what happens when a good client sends a packet. When a good client sends a packet, it is scanned by our firewall. As we can see, it shows that IP MAC check is passed and payload is good, so it can go to the designated server. Now when a bad client sends the packet, it is scanned by our firewall. It shows that it has failed IP and MAC check, so it won't go to deep in packet inspection and it will be rerouted to the honeypot server. There is another scenario in which a bad client can send a packet in which IP MAC check is passed but the payload check is failed, and this will be dropped by our system. Now let's see how our firewall is being controlled by our controller. We have first stage in which is a header stage. We select whether we need to do IP filtering or IP spoofing. Based on the result of the select switch, we go to the next stage, which is a payload inspection stage. If IP MAC passes, then it goes to the deep inspect packet inspection stage. If it fails, it goes to the rerouting stage in the processor. So in the processor, we modify the destination IP and reroute it to the honeypot server. Now let's see how is the packet flow inside our firewall. A packet comes from the network and it goes to core 1 of our processor. Another packet which comes will go to core 2. Now when there is a packet 3 coming up, it will show the core scheduler will be busy and the packet will be stopped in the input queue. Once the packet 1 is done, the core 1 is idle and now packet 3 can occupy its position. Now let's see what's there in a packet structure. The header 1 contains destination MAC, the header 2 contains a source MAC, and there is a source IP in header 4. So what we need is source MAC and source IP to check for IP spoofing. Now let's see how our IP spoofing is being done. In our IP spoofing stage, we form the MAC using header 1 and header 2. The timing of header 1, header 2 and source IP are matched and being compared using a Bloom filter, and it gives us the signal stating whether we need to forward the packet or reroute it. So now let's see how it works. Header 1 comes, header 2 comes. Because we have introduced delay to match the timing of source IP and header. Now it is compared in the Bloom filter. It generates a match signal. Since it is matched, the packet is forwarded and the reroute signal is 0.
Let's see the functioning of a IP filtering system. The IP filtering system makes use of a content addressable memory, the CAM. As you can see, there are a set of IP values which need to be blocked. There are some IP values with don't care terms in it. For example, the 10.star.star.star. This means that the IP filtering system will filter out all the IP values starting with the value 10. There are also corresponding mask values to each IP value. The mask value is 0 for the significant part and 1 for the non-significant part of the IP value. So initially, in the initialization phase, we store the IP and the mask values into the CAM. At this time, the network is not enabled and the values are stored. Now, the network is enabled and we receive the packet. At the same time, the begin packet signal enables the CAM when it receives the IP from the header. The IP value is then compared with the initially stored values, and if there is a match, the match signal goes high. And correspondingly, the IP block signal also goes high. This IP block signal remains high until we receive the end of packet. Once we receive the end of the packet, the D flip-flop is cleared and the system is ready to receive the next packet.
So now we'll discuss how we are doing deep packet inspection using Bloom filters. In this, we have the hardware hash functions and the PRAM blocks. Along with that, we have a software hash generator which is used during the initialization phase. So now I will explain how it is being done in detail. So initially, we need to do initialization of the patterns which needs to be blocked by the filter. So say the pattern is my name, which is Abhishek. So that data pattern goes into the hash generator. So as you can see, it's going into the hash generator. It generates corresponding addresses for the 3 BRAM blocks which we have, and those corresponding bits are set to 1. And we have the write enable, which is also being provided by the hash generator. Now that we have done the initialization, we could do initialization for more patterns also in the similar fashion. Now, if we need to detect the patterns which we have already initialized, say we have the same pattern Abhishek going in as a network data, the pattern goes in the hardware hash function which generates corresponding addresses and it fetches the data which is stored in those locations, and accordingly if a hit is obtained, we obtain the match signal, and this match signal is kept high for the duration of till the entire packet is received, and then it is used to drop the entire packet or reroute it to our honeypot server as per our application. Now we will see how the hash function works. So suppose the pattern Abhishek is there, it gets split into corresponding letters, and accordingly ASCII conversion takes place which generates the binary values, and the least significant bits are used to fetch the corresponding elements from the hash array, and accordingly XORing is done for all the elements to generate the address for the BRAM block.
The following animation illustrates the multi-threading capability of our processor. Our processor is a dual-core, dual-threaded processor. The thread 1 is run in case a spoofed packet is detected and its destination IP needs to be modified to reroute it to the honeypot server. In such a case, we also need to modify the checksum so that the packet is sent through, and which is the thread 2. A comparison between software and hardware firewalls. We have picked up a generic software firewall which is based on SCFA as well as a hardware firewall. The latency advantage can be clearly seen here for the hardware firewall, and we can explain this using the two graphs below. For a software PCAM based firewall, the latency increases linearly with the number of entries, which points to the searching algorithm having a complexity of O of n. Whereas for a hardware Bloom filter based firewall, the complexity is O of 1, which means that the latency remains more or less the same irrespective of the number of entries. Okay, so we have compared our firewall with an existing hardware firewall, which is an NIOS2 firewall. We compare several parameters in terms of their processing latencies. The way we calculate the processing latencies is, first we run the reference router bit file and check what is the round trip time, and then we run our TTT firewall bit file and check what is the round trip time. We take the difference of the two, which gives us the processing latency. It can be seen that the processing latencies for almost all the parameters of the TTT firewall match up with the NIOS2 firewall. But the advantage of our firewall is that it supports two additional features, which are deep packet inspection and IP and max spoof detection, which are quite important. This again just shows performance comparison between the two kinds of firewalls. Although we have a slight performance drop in comparison with the NIOS2 firewall, we think that this is justified by adding more functionality, which is very necessary for security.
Hello. So we'll demonstrate the working of IP spoofing in our hardware accelerator. So this is the router which is already programmed. We are making N0 as the good client, N1 as the bad client, N2 as the good server, and the N3 as a honeypot server. So firstly we'll program our bit file using set underscore ttt.py code. So as you can see, it is programmed. So just to check the functionality, we'll run pinging. As you can see, node is with this IP, and similarly N1 with this IP and N2 with this IP, and so on. So to demonstrate how it is made as a bad client, we are using a SCAPI tool to modulate the data packet header. So as you can see that we will run TCP dump on our server. It is at 4. So we'll start listening it and we'll send the data using our SCAPI tool. As you can see, we are trying to send hello. So this hello is received over here, and it has spoofed the IP address of, as you can see over here, this is the IP address of N0. It has spoofed the source IP address of the guy, and 10.0.2.3 is the destination address. So this is how we are spoofing the IP. So now we'll make a server on this port. With some port 3000, and as our honeypot is also a server, we'll make a server over here too with the same port. Also we can give another port also, that's fine. So if the good client is sending data, if it is sending a good packet, so with the same port, then it should be received over here. It should not be received at the honeypot. So as you can see, the connection is established and there is no problem in sending the data from N0 to N2. But you'll later see that if the N1 is spoofing the IP of N0, though it should receive it on N2, but because of our hardware accelerator, it will be received at N3. So as you can see, the data is sent, but same data, if he wants to send to the same port, it will send the data, and you can see that it is rerouted to here rather than going it over here, but it is using the same IP as that of node 0. So this is how our system works. To demonstrate it using TCP dump, we'll show it even more clarity on this. We'll just clear all the screens. So if we are making a server again on this with some other port, let's say 4000 and 4000 over here too, or let's just open another window for this to listen through the TCP dump. As you can see, this is a node 2 and this is a node 3. So we'll just run our TCP dump on this. This is eth4 and this is eth5. So again, if we are sending the data, now the port is 4000. Now the port is 4000, and if you are sending the data, you can see that the data is getting flooded to the right server as it is the correct client. So there is no problem in receiving over data over here. This is just the LLDP protocol, which is because of the wire connection. And you can see that the data is getting flooded over here. This is a UDP packet without any text file. So you can see the data is getting flooded over here, and there is no problem in sending the data from node 0 to node 2. But if the same thing happens with this bad server, which is N1, which is spoofing the IP address of N0, if it sends the data uh, packet.pl with the same port number, so you will see that the data starts flooding over here rather than going over here. So this is how our functionality works. It is using the same IP as that of N0, and it is thinking that it is sending the data to 2.3, that is node 2, but it is not happening, and he doesn't know that he is being unsuccessful, and that is how our IP spoofing thing works. So we'll just clear all the screens for you. Thank you.
Okay, hi, I will show you the demonstration about IP filtering. So right now I am on the control node and I will show you that I am able to ping to all the nodes successfully. So our system is such that we can block any IP that we want. So let's, for demonstration, let's take N2. We will block the IP of N2, which is 10.1.2.3. So for blocking, we have a script which will program the hardware accelerator with the blocking IP. So you need to enter the IP to be blocked in hexadecimal. So I will enter that in hexadecimal. Okay, so now IP blocking is a program with N2's IP to be blocked. Let's try pinging to N0 first. As you can see, we are able to ping successfully. Let's ping to N1. Now try with N2. As you can see, since we have blocked the IP of N2, we are not able to ping to N2. Okay, let's do the same thing. Let's see if in server client environment, if we are able to block the communication to N2. So let's set N2 as a N0 as a server. Let's select the port as 2000. Now from N2 I will try sending one packet to N0, but since I have blocked N2, it won't be able to send anything to N0. Okay. I'm giving the server name over here and the port number. As you can see by the warning, the IP or the communication from N2 is blocked. Now I will try sending one packet from N3 to the same server, which is N0. As you can see, since N3 is not blocked, we are able to ping to the N0 successfully. Let me change the IP again to be blocked. Again, I will use the same script to change the IP to be blocked. Okay, let's block N1 this time. So the IP for N1 is okay. Now I will just show you the pinging and I will show you that N1 is blocked. So as you can see, N1 is blocked this time and communication to N2 is restored. I will give you the demonstration for deep packet inspection. In deep packet inspection, we are using Bloom filter. So for Bloom filter initialization, we have a software script which will initialize the hardware Bloom filter with the patterns that we need to match. So I will run the script first. So the name of the script is bloom_init.py. So it is asking me if I want to use the predefined patterns to program the Bloom filter. So what exactly is the predefined patterns? So we have a list of patterns which we have already defined in our notepad file. So as you can see, there is December, there is internet, there are all kind of words in this file. So I will just put Y over here and program my bloom filter with all the patterns in the notepad file. But remember, at the same time, we can add any number of patterns if we want to. So this is the functionality check. So we will check if our bloom filter is programmed with the patterns that we defined in the notepad file. So I will just put 3 over here. I will check it for, let's say, 4 patterns. So I will enter internet. You know that the internet was already there in the file, so it's saying pattern matched. Let's try with Nicholas. You can see it up above that Nicholas is also there. Then let's do December. Same pattern match. Now I know the word Abhishek is not there in the predefined pattern, so let's try for Abhishek. It will give me pattern does not match. So this basically says that the bloom filter is programmed correctly. So now I will make the N2 as my server and N0 as my client, and I will try sending packets from N0. And if my bloom filter is working correctly, and if the packet has the data which I need to be filtered, it will block the data. So let's set the N2 as my server. So let's take the port as 2000. So it is listening on port number 2000. I will make this as my client. So I will give you the N2 and 2000. So you can see the packet got through. Now we will do the TCP dump on the node N2 to see the what data we are receiving on the node N2. So let's go to the another window of N2. Okay, let's run the TCP dump over here. So this is Ethernet 4. Okay, so now the node 2 TCP dump is running on N2. Let me again send the same packet on N2 and see what happens. Okay, so the packet got through, and we can see the data that we sent to our file. So yeah, it was a let's go up. Yeah, it was, yeah, you can see that the word Abhishek is coming through the file. Okay, now I will add one pattern in this file which I need to be blocked, which is already programmed in the bloom filter. So let's go to the notepad and change the pattern that I am sending. So initially there was Abhishek. I will just delete this, and instead of Abhishek I will use the word internet, which we know that is present in the bloom filter. So ideally it should be able to block this packet. Let's transfer this file using FileZilla. Now okay, again I have to make the server on N2. Let's choose 2001 this time. So as you can see, since the file had the pattern which needs to be filtered, it is not going through. So in this way our bloom filter is successfully filtering all the packets which has the patterns which we need to be filtered. So this is the demonstration for deep packet inspection. Thank you very much.
I'm now going to demonstrate how we compute the average processing latencies for a firewall. First, I'm going to load the reference router bit file and ping from node 0 to node 1 and check for the average round trip time. Okay, so we're gonna run this just once again to make sure it's the right value. Okay, so the average round trip time observed is 0.185 milliseconds. Now we are going to run another script which will load our bit file, which is a TTT bit file, and check for the same. Okay, so as we can see, the average round trip time here is 0.186. So the difference is around 1 microseconds, which is very close in this case, but on average it comes out to be around 4 to 5 microseconds.
Okay, now I will explain you the NIS2 hardware firewall. This is the firewall which we use to give to benchmark our system. The functionality of this firewall is destination port filtering, source IP MAC address filtering, source IP and destination port based filtering, MAC address based filtering. Whereas our firewall gives IP based filtering, IP MAC spoofing, and deep packet inspection based using Bloom filter. We selected this firewall because the architecture of this firewall is very much similar to the architecture of our firewall. As you can see, the architecture of NOS2 hardware firewall contains CAM, NetMask RAM, which is almost similar to our firewall. Now let's see how we measure the throughput of our system. For measuring the throughput, we'll first load the reference router, create N2 as a server with port 4000, and we'll start a script which will measure the throughput of our system for the reference router. Initially we executed this script and got the following results. So while the script is being executed, we can see what are the results. So here there is a graph of drop rate versus bandwidth. As you can see, the drop rate of our firewall is almost comparable to the drop rate of a reference router. The drop rate of a firewall is 0.52 at 835 Mbps, and the line speed is 1 Gbps, whereas the drop rate of reference router is 0.048%. The difference in this drop rate comes due to the processing latency. Okay, so now we can see that for reference router at 619 Mbps, the drop rate is 0.027%. Okay, now it will go, the script is being executed for bandwidth from 100 Mbps to 1 Gbps with the increment of 200 Mbps. Okay, at 839 Mbps it's 0.062. At 929 Mbps, the drop rate for reference router is 2.9%. Okay, so now we will load our bit file. Stop the circle over here. Okay, this will load a bit file onto the NetFPGA. Now let's create N2 as a server. We'll again run the same script to measure the throughput of our system. In this bit file we have selected the functionality of IP filtering and deep packet inspection, which would be the worst case scenario for our system, because deep packet inspection gives the maximum latency, hence it uses the maximum processing time, and that will affect the throughput. So we are reporting the worst case of our firewall and comparing against the reference router. So at 405 Mbps our drop rate is 0.02, which is very less. At 619 Mbps it's 0.03%, which is very good. We have used UDP protocol to send the packets. At 839 Mbps our drop rate is 0.083%. And at 843 Mbps our drop rate is 12%. So as you can see here, we can report around 835 to 850 as the bandwidth and the throughput of our system, the maximum throughput of our system.
This concludes our presentation for TTT Hardware Firewall. Thank you for watching our video.